Good evening, everybody, and welcome to the second Milne Lecture. The Milne Lecture are annual talks that are supposed to provide a glimpse into the future by providing some of the most exciting advancements in engineering and considering how these will transform our world. And I'd like to quote Dr. Milne, whose generosity has created this series. When he was starting this out, he said, "I am delighted to enable Edinburgh's renowned School of Engineering to connect more people with the greatest and most exciting engineering developments that are happening today. I hope these lectures will provide a better understanding of our modern world and encourage the next generation of creative minds to contribute to technology advances." So that gave us quite a high bar to meet, but I'm very happy this evening to introduce our speaker, Professor John Rogers, who will talk to us on frontier developments in bioelectronics. Professor Rogers is the director of the Querry Simpson Institute for Bioelectronics at Northwestern University and the Louis Simpson and Kimberly Querry Professor of Materials Science and Engineering, Biomedical Engineering, Neurological Surgery, Chemistry, Mechanical Engineering, and Electrical and Computer Engineering. So his career has taken him to MIT, to Harvard, to Bell Labs, to the University of Illinois, Northwestern, and of course, we are delighted to have him here this evening to deliver the Milne Lecture. I wanted to say a tiny little bit about bioengineering, first of all. It sits at the intersection between different engineering disciplines, the physical sciences, and medicine. And Professor Rogers is a world-famous pioneer in this multidisciplinary research space that brings together these disciplines and explores possibilities for new technologies with the potential to have a profound impact on healthcare. The new devices that John and his group are developing include skin-like devices for health monitoring and bioelectronic medicines for neuroregeneration and temporary cardiac pacing. Now, this is a particularly exciting area of engineering, with new ground being broken by research groups such as John's, as well as by researchers in our own Institute of Bioengineering, where solutions to important engineering problems have enormous power beyond the lab to tackle some of our biggest societal challenges. So our newly recruited head of the School of Engineering, Professor Guanxiao Mao, is an expert in bio-nanotechnologies, and Professor Adam Stokes has recently taken over leadership of the Institute for Bioengineering, which is a key area the university is developing, with areas such as biomechanics, industrial biotechnology, engineering biology, tissue engineering, and biorobotics. And just as an example of some of the work going on, we've just launched a new postgraduate program in this area, an MSc in biomedical engineering, and we have recent funding success between Ian Underwood and Kev Dhaliwal's new £27 million program, Microtex, which aims to speed up the creation of new treatments for lung infections and inflammation, which are among the leading causes of illness and death. So these types of synergies between labs, collaboration and sharing of ideas are key to driving forward the new ideas and discoveries that have the potential to shape our world. And lectures such as this, therefore, inspire us all and allow these conversations to happen and capture the spirit of what David was looking to achieve. So, without further ado, Professor Rogers, please. Thank you.
Okay, great. Yeah, well, thank you so much for that kind introduction. It's a real pleasure to be here. I want to start by thanking David Milne for making this lecture possible. It's a real honor to be here and be able to speak in the context of this lecture, because I think David kind of embodies a lot of what we aspire to do in terms of commercial translation and broader impacts beyond just academic science, and you'll kind of see that as I step through the slide deck that I put together for you. So things that are really, at a high technology readiness level, FDA approved and deployed, at meaningful scales and sort of headed in what we think is the right direction, but there are many ways, that these things can run into difficulties, but we're very optimistic about where things are headed. So it's great to meet David, and I look forward to having some additional conversations with you over dinner to talk about that commercialization process, because it is something we're very interested in. So this is my first time to Scotland. It's my second day in Scotland. I arrived yesterday afternoon and immediately went to University of Glasgow to give a talk there. So I had a chance to meet the faculty, see the facilities, and they were big on the idea that they're actually a lot better than you guys, university. And so I figured, well, I'll see for myself, because I'm spending the day with you guys today and tomorrow. And I have to say I'm extremely impressed by everything that I've heard, that's going on here from a research standpoint. And it turns out I actually know a fair number of people here at University of Edinburgh, starting with Adam Stokes, who invited me, and we spent some time together in a similar lab at Harvard, so we have some connections there, similar perspective as a result of that experience. But Alan Murray also reached out maybe 6 months ago, and we started collaboration. We actually have a joint proposal together, so fingers crossed that gets awarded, then we'll do some collaboration, get you out to Chicago, and maybe do some exchange and so on. And Ewan Harrison actually is somebody that I've interacted with. We actually spent a week in Africa together about a few weeks ago, and I'll highlight a little bit of that in my presentation. So it's really that medical interface that drives a lot of our choices and engineering priorities around the research topics that we pursue in my group, and hopefully you'll see that kind of flavor as I step you through the content. So as was mentioned, I'm director of this Institute for Bioelectronics, and I know that's an area of great interest here, and Adam and others are really kind of spearheading some fantastic programs in that space. It's also been an area that we've been interested in and active in, for a number of years, probably 15, maybe almost 20 years, depending on when you mark the starting point. And so I'll give you a sense of what we're doing. The Institute is also very translational in the sense that it's set up to really facilitate research at the boundaries between engineering science and medical science, ultimately clinical practice as well. And so almost all of our work involves intimate collaborations with the medical community in Chicago, not just our medical school, but the broader medical complex downtown Chicago. And we can get devices deployed on actual patients in pilot scale studies as a precursor to moving things out of the academic lab. Those ideas that work well and are actually offering a benefit to patient care. So that's what I'll share with you today. And it's probably 45 minutes of content here, but I'm more than happy to engage in discussions and questions and answers after the presentation. And I have a few demos and widgets I'll pass around in a little while to give you kind of a hands-on sense of the technologies that we're interested in. So it's kind of the frontiers of what we're doing in bioelectronics. Obviously, the frontier is a little bit broader than my own group, but it's kind of areas that we've been pursuing, over the last dozen years or so. I'll begin with kind of a background, motivation, context around what we're hoping to do in a broader sense, give you an idea of kind of the materials and the devices and the manufacturing approaches that have worked well for us to support this kind of technology, and then focus on how we're pursuing them at a research level where we think we're building the foundations of things that can translate and be used to benefit patients ultimately, and things that are already in that direction. So research and medicine is kind of what I'll try to share with you today. So what we're really interested in is the development of technologies that can live in intimate contact with living systems, biological systems specifically, and trying to develop levels of sophistication in those technologies that match the kind of capabilities that are in widespread use in consumer electronics gadgetry, industrial electronic systems, but reinvented with new classes of materials, new fabrication approaches that allow us to impart sort of biocompatible sets of physical and chemical characteristics to those devices. And we think about developing the technology, but then understanding what points of interface that kind of technology could be useful for in the context of human health care. And I think it's easiest to consider that set of opportunities in the context of the human brain, which is biology's most sophisticated form of electronics. And if you want to understand how the brain brain operates from a fundamental level, or you want to develop engineering approaches to treat brain disorders, maybe you would like to bring to bear to that problem man's most sophisticated form of electronics, the silicon integrated circuit. But immediately you realize there's a huge mismatch between the physical and chemical characteristics of the brain and a silicon chip. And so that sets the stage for a number of what we find to be very, very interesting academic research topics whose solutions could lead to technologies of broader utility for not only interfacing to the brain for fundamental research purposes, but also, as I mentioned, for therapeutic function. But also you think about those same kinds of platforms, if you can make them in geometries and with mechanical properties and chemical characteristics that would allow for interfacing with the brain, you'd think about other points of interface to internal organs of the body. We've done a lot of cardiac interface devices. I'll talk to you a little bit about that maybe halfway through this presentation, but also devices that interface with the peripheral nerves, the spinal cord, the bladder, the kidneys, the liver, the diaphragm, all sorts of points of integration that we've explored over the years. But maybe the lowest hanging fruit in terms of commercial translation and FDA approval would be interfaces to the surface of the body, so the body's largest organ, the skin, and thinking about skin-like devices that could interface with the skin and exploit the skin as a window for measuring fundamental underlying physiological processes as indicators of health status. So what's the challenge there? I already tried to highlight those challenges. Why don't you just take a step back and make a few very obvious observations of man-made micro and nanosystems technologies. And we're not just talking about integrated circuit technology, but optoelectronic systems, microelectromechanical systems, microfluidic lab-on-a-chip type devices, incredibly sophisticated for the applications for which they were originally designed, but with a set of engineering characteristics that are basically sort of common across all of those different platforms. They're planar in their geometry, and that's of advantage due to the fact that photolithographic processes can project onto a planar surface, and they're rigid, made out of hard materials, primarily silicon, silica, copper, gallium nitride, that kind of thing. They're static from a functional standpoint, and from a physical standpoint, they're not active in that sense. And from a geometrical layout, they consist mostly of two-dimensional, dense, multi-layer stacks. And again, those are great engineering choices for conventional electronics. But if you think about bioelectronics, you might want to develop technologies that have characteristic engineering features that you see in the living world, rather than in traditional man-made microsystems technologies. And what would those features be? Well, you think about neural circuit maybe as a rough biological analog to an integrated circuit. It's totally different. Or you think about a vascular network in the context of the brain, as illustrated here, as an analog to a microfluidic lab-on-a-chip type technology. It's totally different in the sense of the geometries. These are curved systems. They're mechanically compliant. They involve blends of hard and soft materials together. And instead of these dense 2D multi-layer stacks, they exist in open 3D frameworks. And so if you want to develop integrated electronics or bioelectronic systems, you'd like to be able to build technologies that have those kinds of characteristic features to make the technology look more like the biology to enable that kind of integration. So just to restate what we're attempting to do is we want to take a technology like the silicon integrated circuit and reformulate it so that it can be integrated in, on, or around soft living tissues to sort of blend the distinction between the technology and the biology to allow for continuous two-way communication with chronic stability. And you might want to do that in the form of permanent or temporary or static or dynamic types of systems to sort of accommodate variations and healing and so on, processes that occur naturally in the living world. So let's talk then about what a skin interface device would look like. And this goes way back, actually, you're thinking about this before conventional wearables even existed. You know, the Fitbit wasn't even around at this time. We were part of a DSRC study group thinking about a future of electronics that would allow soft tissue integration and thinking in the context of the skin, but with sets of design principles and material elements that would allow for integration with the brain or other kinds of internal organs. So we thought about the notion of epidermal or skin-like electronics, and what would that look like? You'd want the electronics to be as thin as possible, so we thought 5 microns in total thickness would be a useful goal to think about. In terms of areal mass density, ultralight to eliminate inertial effects. It could otherwise disrupt adhesion at the device-skin interface and maybe cause irritation. as low as possible in terms of the modulus. So we thought, maybe 5 kilopascals, much lower than the skin, but the lower, the better in terms of mechanical compliance. Devices that could not only flex, which is an important sort of mechanical characteristic that goes beyond what's possible with a conventional silicon integrated circuit platform, but also stretch, which is a different kind of mechanical characteristic, more like a rubber band, because the skin itself stretches. And so to be able to accommodate natural deformations of the skin, you would want a technology that not only bends, but stretches. And then additional characteristics you might want to think about, you want the device to be air and water permeable to allow for the transmission of transepidermal water loss and to avoid the buildup of biofluids and sweat and so on at the interface between the device and the skin. But at the same time, you'd like to waterproof the electronics to eliminate corrosive effects that could otherwise follow from interaction of active materials with the surrounding biofluid. So that's what we envisioned and hoped to achieve way back in 2008. And so it was sort of a kid's temporary tattoo version and vision of an electronic system. And so then the question is, how would you go about achieving that vision? And you could think about two separate paths conceptually. You might take a look at a silicon microchip and conclude that silicon is never going to work for that kind of application. The modulus is too high, it's mechanically brittle, you can't bend it, you certainly can't stretch it, and maybe you have to move to alternative semiconductors as the basis for that kind of technology. So maybe polymer-based semiconductors, or maybe carbon nanotubes, or graphene 2D materials, a whole host of options you can kind of consider. And if you were going to go down that path, and we spent a lot of time thinking about that and working in that direction, you'd have to think about what kind of performance you could achieve, thinking about practical levels of functionality, and also how you would do manufacturing with all of those different novel electronic materials. And I think it's a very promising path to consider. But the other approach would be to say, let's stick with the known materials, but blend them with unconventional materials and sort of hard, soft composites that could give you the kind of geometries and mechanics that you would ultimately hope to achieve for this sort of biocompatible level of integration, but with materials that serve as the foundations for high-performance devices where there's a deep base of scientific knowledge on how to grow the materials and process them and build high-performance devices, and also in the context of material classes that would allow you to tap into the incredible manufacturing infrastructure that's built around silicon CMOS technology. And so these are the two simple ideas that have worked well for us along that conceptual path to development of a bioelectronic platform. And so very simple ideas and mechanics. I'm not going to belabor the concepts. It should be pretty obvious. One is to recognize that the silicon wafer is rigid and brittle, partly because the silicon has those intrinsic properties, but also partly because the wafer is pretty thick, maybe a millimeter in thickness. And if you take any material and you reduce the thickness sufficiently, the flexural rigidity reduces with the cube of the thickness. So you take silicon wafer and you figure out how to slice off the near surface region of that wafer, nanoscale forms of silicon, in this example, nano ribbons of silicon. The thickness is so small that they become mechanically flexible and floppy, much different than the properties of the silicon wafer. And you can think about those nano ribbons then as building blocks that you can integrate with a sheet of plastic to begin to construct high performance monocrystalline silicon electronics on a flexible substrate. And that could be of separate interest. But as I mentioned before, if you have a system that can just bend but not stretch, it's very difficult to conform to complex geometrical surfaces associated with the surface of the body, and you can also not accommodate the natural motions of tissues, which involve large elastic responses to large strain deformations, totally different than bendability. So you can't make silicon thin enough to make it stretchable, but you can take that thin silicon and then mount it onto an elastomeric substrate, but you do that not in a flat geometry, but in kind of a wavy shape. And that wavy geometry allows for an effective end-to-end stretchability where the geometry of the wave structures can change to accommodate that large strain deformation through changes in the wavelength and the period. So just like in accordion bellows, if you stretch out that hard, soft composite in that particular type of geometry, the wavelengths go up, the amplitudes go down to avoid any kind of fracture-inducing strain in the silicon itself, but you get an effective mechanical property that's really dominated by the underlying elastomer. So very simple ideas, but they turn out to be ideas onto which you can add all sorts of engineering elaborations to begin to do real system-level development. So for example, you don't have to think about this out-of-plane wavy shape. You don't have to think about just individual isolated ribbons of semiconductor material or active devices. You can think about interconnected 2D mesh structures in these kind of filamentary serpentine geometries where you're exploiting not only out-of-plane wavy shapes, but in-plane wavy shapes as well. If you take that kind of architecture and you layer on top of it quantitative finite element modeling of the integrated mechanics of these hard mesh structures with a soft elastomeric surrounding matrix, then you can quantitatively and in a precise way engineer the shapes of those filamentary serpentines so that when they are integrated with a soft elastomer, you can achieve stress-strain characteristics that can be dialed in to match those of a tissue onto which you would like to integrate the electronics. So in this particular case, the stress-strain behavior is very similar to that of skin. So it's an effective modulus about 150 kilopascal, in spite of the fact that these filamentary serpentine structures include materials like silicon, which has an intrinsic modulus of 150 gigapascal, so 1,000,000 times stiffer than the effective properties of this hard, soft material composite structure. So that turns out to be interesting. The other thing that this kind of architecture affords is the ability to conform to a topologically complex surface like that of the skin or the heart or the brain, not just a flat surface, but something that's very textured. So this is a polymer replica of human skin onto which we've dropped one of these filamentary 2D mesh structures, and you can see how that kind of geometry allows for conformation of that complex surface in all of the regions except those associated with the most extreme levels of curvature. Now that's important from the practical standpoint of adhesion strength. You would like a large contact area to allow for robust integration and adhesion to the surface of the skin. But if you want to include sensors in that mesh, that level of contact is also important because it reduces the interface impedance associated with the various kinds of measurements that you might want to make. Again, using the skin as a window for measuring underlying physiological processes. So that's basically it. That's all I'm going to say about the foundational engineering concepts. Many, many papers we published. Lots of other groups have been very active and contributing in a really powerful way to this kind of strategy toward bioelectronics. And so when you put it all together, you're really thinking about system design at three levels. One is material selections. What are the active materials that you're going to need to embed in your system to achieve the properties you need or are striving to achieve? You think about mechanics designs, how you lay out this class of material in this sort of circuit layout, not only from a functional standpoint, but from a mechanical standpoint as well. So from a material science standpoint, you think about it as a hard, soft, sort of hybrid material system that offers circuit level functionality to address real requirements. So starting about 2016 or so, we felt like we had a pretty good handle on how to do all of that and began to wonder, what kind of applications could be satisfied? What would be the capabilities that one could exploit in the context of medical care and patient care? And we decided that premature babies would be a compelling opportunity for use of that kind of skin-like, ultra-thin, soft electronics because that class of patient requires 24/7 monitoring of all vital signs, currently done with technologies that were originally developed to monitor vital signs of adults in ICU settings. So it's really poorly suited to these very precious but fragile babies, these premature babies. So it's tapes that affix hard sensors to the surface of the skin, hardwired connections to external expensive boxes of data acquisition electronics for doing all of the monitoring. And that happens 24/7. So it really creates a constraint and a set of difficulties even in the most routine processes in clinical care. It also frustrates the ability of parents to interact with their child because they're all wired up. And the tapes, in many cases, because they have to provide adhesion sufficiently strong to keep the biosensor in place as the baby's moving around and forces are imposed on that interface through those hardwired connections, those tapes, applying them and removing them, typically on a 12 to 24-hour cycle, can lead to damage of the skin, which is, in many cases, underdeveloped for these premature babies. So the vision was to do this. This was just a Photoshop illustration of what we were hoping to achieve, which we generated back in 2016. But we spent a lot of time and effort in that direction, and I'll just state the end outcome of all of that is that you can do that, in fact, take the engineering principles I just described to you, put together systems that match all of the requirements in vital signs monitoring, even in very sophisticated level 4 NICU units that we have here, or in the US and here in the UK and various parts of Europe. So these are the devices. We published this in spring of 2019. The device resting on On the fingers there is a patch that goes on the chest. So it's wirelessly powered. It's wirelessly continuously streaming data. There are 2 electrodes that allow us to do single lead ECG, so we can get heart rate variability, and respiration rate from that data channel. There's also a precise digital temperature gauge embedded in that device, so we can get skin temperature from the chest, which is a pretty good approximate for a surrogate for core body temperature. The other device is resting on the palm, and that provides 2-color photoplethysmography, and so from those data streams we can infer blood oxygenation. That sort of fills out all the vital signs that are continuously monitored in this particular context. So we're able to get IRB approval to insert those devices into an operating NICU at Lurie Children's Hospital in downtown Chicago. At this time they weren't FDA approved, so we needed to keep the wired devices in place as well, but that turned out to offer a great opportunity for quantitatively comparing the data streams we're getting out of our skin-like wireless devices to the conventional wired-based systems, and that's kind of what you're seeing there. That's a premature baby at Lurie Children's. The hand that you're seeing on the right side, that's Aaron Hamvas, who's head of neonatology, so we established a great collaborative rapport with his department, the nurses, the neonatologists, and so on. So that's what it looks like. We're not really a software group, but if you want devices of this type to really enter into sort of somewhat routine use in a NICU facility, it needs to be compatible with the nurses. And so you need to generate graphical user interfaces that look exactly like the interfaces they're used to using in the monitoring systems provided by Philips and GE and others. And so that's what we've done here. This particular device is operating in a wireless fashion, communicating data to an iPad is what you're seeing there. This particular baby is a 26-week delivery. So commonly the 24-week delivery period is known as the edge of viability. So this is about as young of a premature baby that you would encounter in a NICU facility. And so we did about 200 babies through Lurie Children's without any adverse effects, and we're still interacting with those groups, testing new types of sensors. We start with replicating the kinds of monitoring approaches that are used as a routine part of clinical care in a facility like this. But now you have an electronic platform, you can think about de novo capabilities as well, and that's kind of where our research focus is at this point, and I'll give you a couple of examples of that a little bit later. So we had great success in the NICU. We actually migrated beyond the NICU into the PICU, so this is slightly older babies. This is the pediatric intensive care unit, not only at Lurie Children's, but also Princess Women's Hospital, which is also downtown Chicago. This is an example of a device deployed on a baby in the PICU at Princess Women's Hospital. You can see the device on the chest. That's the one that's doing single lead ECG and temperature measurement I mentioned before, heart rate variability, respiration rate. And then the unit that's doing 2-color photoplethysmography is down here on the foot. And so we do reflection mode PPG to get the blood oxygenation out from that device. So they're battery free, so they're being powered using magnetic inductive coupling from an antenna that sits in the base of the chair. And that same magnetic inductive link is using for RF backscatter based approach to wireless data communication. The devices are also time synchronized. And so you get some hemodynamic information as well, because you can measure when a pulse of blood is initiated from a cardiac cycle and when that same pulse of blood arrives at a distal location, in this case the foot. So you get pulse wave velocity, which in some cases can be used as a surrogate for blood pressure if appropriately calibrated. So I mentioned that the Institute is really set up to drive research at the boundaries between engineering science and medical science, and this is sort of an example of kind of a success story, I would say, for that type of effort. So this is spring of 2019. It was like 45 co-authors across all traditional fields of engineering science, but as I mentioned before, interfaced intimately with the medical community. So there's head of dermatology, head of neonatology, head of pediatrics are co-authors here. But what we found is the most important medical professionals to interact with are the nurses, because they really have a hands-on feel for what works and what doesn't in a real clinical environment. And so we also engaged with the nurses and took a lot of their feedback in terms of engineering design choices. So that was spring of 2019, just to give you a story here. So shortly after that paper published, it captured a lot of attention in the popular press, as you might imagine. And so I was contacted by program managers at the Gates Foundation and the Save the Children organization. They asked whether we could adapt those technologies for deployment into lower and middle income countries as well. So we can make monitoring capabilities present in parts of the world where no monitoring is done at all. And so that created another sort of compelling engineering challenges. How do you do engineering around not just traditional performance specifications, but how do you engineer for cost? And thinking about low cost as additional kind of performance metric in a sense. And so we had to make a number of changes to the devices to develop economic models around the technology that would suggest economically viable deployment into these challenging regions of the globe. And so we're able to do that with support from the Gates and from the Save the Children organization. We're able to publish adapted versions of those same devices, but with engineering features and with alignment with manufacturing capabilities that allow us to get into a cost structure that was pretty reasonable. So we started with deployments in India, Pakistan, Zambia, Kenya, and Ghana around the end of 2019, and we've continued to the present day. And as I mentioned, I was in Africa with Ewan Harrison. He's very much part of these studies at this point, funded by Wellcome Leap Foundation as well as the Gates Foundation. So these are some of the data streams that come off of these devices, raw data in the top frame there. So you see electrocardiograms at the top blue trace, two color PPG. Those are the next two traces, red and near infrared, pretty standard. And then we also, in this particular device, embedded sort of a de novo capability in terms of monitoring in the NICU. It's a high bandwidth accelerometer that allows us to do cardiac auscultation. So we're measuring cardiac sounds with that device. That goes beyond standard of care, even in a level 4 NICU in the US. And that provides complementary information to what you can get from the ECG reading. And it also has enough bandwidth, you can actually get bulk movements of the chest wall, so you get a good estimate of respiratory rate as well. So the physicians are really not interested in the raw data. I think there's a tremendous amount of information that can be mined from the raw data sweeps. But really, they're looking just at some extracted parameters, very simple parameters: heart rate variability, SpO2, respiration rate, and temperature. And so that's what we're providing to them currently, but I think there are a lot of additional insights that can be extracted as an area of opportunity. So that's what it looks like. This is the first deployment. This is a picture from a couple of my students in the front of a room training a collection of healthcare workers in Zambia. So that was December 2019. It was about at that point we decided we really couldn't support that level of deployment and engagement through graduate students. And so it became kind of a forcing function for us to put together a very engineering, sort of product-oriented startup company called Cybele Health. And I'll tell you a few more things about Cybele Health here in a second. And they're running all of the Gates and Save the Children programs and Steel Foundation for Hope and a number of foundations that are supporting the work. But these are some pictures from the most recent trip. I don't know if Ewan, you're featured in these pictures or not, but he was with us in many of these trips and visits. This was Lagos, Nigeria. We were in Kigali, Rwanda, and Nairobi, Kenya for about a week. And so instructing healthcare providers on how to use this technology and deploying it sort of at a meaningful scale. So in order to do that, I said, before, you really need a startup company as a vehicle, but it's non-traditional startup in the sense that the focus is not on exit strategies and pitch decks and VC funding, but rather partnerships with large medical device providers. So we have investment and partnership with Draeger, for example, Space Labs, and they have a global, health thrust as well through Gates and other foundations. So a number of FDA approvals. These are kind of the numbers of sensors that have been deployed. I think it's 20 countries at this point. Almost 10,000 sensors have been deployed, and so moving in the right direction. Very very excited about this, and I think we're gaining good traction in that direction. So I have a couple of the devices that are being deployed, just so you can kind of get a sense of these. I'll pass these around just so you can sort of check them out. These are not free samples, so I need these back. I'll just give you a sense of the kind of mechanics we're talking about and the form factor and sort of the soft silicone. And it turns out that I'm wearing one right now. I didn't mount it up specifically for this presentation, but I'm testing out a new adhesive, and so this one's been on for 6 days, I think. I've done a couple of workouts, a number of showers during that time. You don't have to worry, I do daily showers. Anyway, so it's continuously recording. It's FDA quality, clinical quality, single lead ECG, and accelerometry, so we're getting cardiac sounds as well, so you can come by and check it out if you want. It works quite nicely. So this is kind of what's going on from a translational standpoint. But back to research that's happening in the group, in the lab, we think there are a lot of opportunities for new technologies to address early life health challenges. So we're really focused on pediatric neonatal health, but also maternal fetal health. And so that's kind of a main set of patients that we're focused on. So we have flow monitors for kids with shunts that are used to treat hydrocephalus, pediatric NERS. We have maternal fetal monitoring devices. That's now part of a large Gates-funded program, so measuring health of the fetus, health of the mother during the intrapartum period, respiratory, GI monitoring, EG, and then we also measure transepidermal water loss, transcutaneous CO2, and eccrine sweat as a novel biofluid for biomarker detection and biochemical measurements of health status. So that's kind of a summary of what we're doing kind of at the medical interface directly, where we're really going through regulatory processes and manufacturing and scale and that kind of stuff. For the rest of the talk, I'll give you a direction and a set of research activities that we feel are promising, but a little bit more into the future. So these are more sort of focused in the academic realm. And let me describe to you the motivation, but this kind of research forms the basis of the proposal that we wrote with Alan Murray. And so there'd be a good opportunity to work collaboratively in this area. So as I mentioned, these kinds of design principles allow you to generate skin-like electronics. You put it on the skin, but you also put it on the brain. You can put it on the heart. You can put it on other internal organs. And we've done a lot of work in many different points of integration and different envision clinical uses. You think about implants in this context in two ways, defined by the time of integration with the organ surface. At one end of that spectrum, you think about these kinds of devices as surgical diagnostics or surgical tools, where the interface needs to persist for the time of the surgery, which could be a few hours, kind of in that realm. And so we work with Brian Litt at University of Pennsylvania, thinking about micro-ECOG arrays to monitor electrophysiological activity on the surface of the brain, to define aberrant regions of the brain that need to be resected to treat certain forms of epilepsy. In that case, the device just needs to be there a few hours, maybe a few days. Then you pull it off, you use the information to know what part of the brain you need to remove. So there's a whole set of applications in that surgical context. And then at the other end of the spectrum, in terms of time for integration, you think about permanent implants. So maybe this kind of cardiac interface device, sort of like an instrumented pericardium going around the outside surface of the heart to provide spatiotemporal mapping of electrophysiological activity, and then sort of visioning things in the future. Think about how you might do spatiotemporal pacing of the heart, stimulation of the heart to eliminate an arrhythmia before it becomes a problem, just as a vision. And so in that kind of context, you think about residence times that would be measured not in a few hours or a few days, but a few decades. And maybe from an engineering standpoint, you want it to last the life of the patient. Maybe you engineer it to last for 100 years of stable operation in biofluids, so warm salt water. So that's a whole set of other challenges that turn out to be really interesting and daunting ones as well. We're interested in both of those classes of application. What we didn't realize when we first got involved in this area is there's a whole set of applications in between those two limiting cases where you might want an implantable device to go inside the body, provide some kind of diagnostic or therapeutic function, but only in the time scale of a transient natural biological process. Let's say recovery from a surgery or healing of an internal wound. You might want to monitor, you might want to stimulate to accelerate rates of healing. But then ultimately, once the internal wound is healed, you don't need the device anymore. And so you have two options. One is you go in and you do a secondary surgery to extract the device to eliminate what at that point would represent unnecessary device load and risk to the patient. The other possibility is to try to design the electronics so that they would just naturally melt away and dissolve away entirely. And so with that kind of vision, you're thinking about an electronic form or an electronic analog to a resorbable suture, which provides just a simple mechanical function in the context of wound healing. And then once the wound is healed, the suture is just designed to naturally resorb. So could you do electronics with that key defining characteristic of resorption? And so then you're back to asking the question similar to the one that I asked before, but now not in the context of redefining the mechanics of a silicon integrated circuit. But the question is, how do you generate a water-soluble integrated circuit? Like how would you do that? Water-soluble, meaning it would dissolve naturally in biofluids to biocompatible end products, but at the same time with the capacity to support the sophistication and function that you're familiar with in a conventional wafer-based class of electronics. And so again, you're faced with a decision. Are you going to develop a whole new class of materials? Maybe you exploit the chemical diversity in polymers to develop a material that supports good charge transport characteristics, but also could undergo hydrolysis and chain scission when exposed to water, and maybe you can kind of go down that path. You have to worry about the same kind of issues I mentioned before. What about performance? What about stability? What about ability to do integration and manufacturing? And you can kind of go down that path. And again, we spent a lot of time thinking about that. But then the other path would be to ask whether you could somehow use silicon for this application. And you might sort of initially think silicon is never going to work, and silicon integrated circuit technology is never going to work, because all of the engineering emphasis that has been built around this class of technology for consumer electronics and industrial electronics applications has been to design the devices to last forever with no change whatsoever. And so we're asking something much different. We're saying we don't want it to last forever. We want it, in fact, to disappear in a biocompatible way. So you might think, this would be a terrible starting point, silicon. But then we lucked out because I had a really observant postdoc. We're playing around with a lot of these silicon nanomaterials that I mentioned before, like these filamentary serpentines, these ribbons, these membranes, and so on. So super thin, maybe 50 nanometers in thickness. And what he observed is that when he tried to harvest a lot of silicon material in that nanoscale form, so we can go off and build flexible and stretchable devices, if he left them in a beaker of water for more than a few days, they would just disappear, just totally gone after a period of time. And that's kind of what's illustrated here in these upper frames. This is AFM images of a nanoplatelet of silicon. So it's a couple of microns on a side, about maybe 100 nanometers in thickness. And it's just immersed in water. In this particular case, it's water buffered to a physiological pH, so it's very slightly basic, and at physiological temperature, 37 degrees C. And what you see is you just measure it at various time points, it just dissolves away, it's gone. And if you measure the height of that nanoplatelet as a function of time, you see that it dissolves at the rate of a few nanometers per day, so almost nothing. You would never really observe this in a wafer scale piece of silicon, but in these nanomaterials, you can't avoid it. So in this case, it dissolves completely in about 3 weeks. So extremely slow chemistry, but very important chemistry, because it eliminates the silicon. And furthermore, it turns out that the chemistry is very simple. It's just silicon reacting with water to form silicic acid and a little bit of hydrogen. And the lucky thing here is that silicic acid is naturally occurring in biofluids and groundwater, so it's biocompatible. It's only a small amount of material anyway, because you're starting out with a nanostructure of silicon, a tiny amount of hydrogen which just dissolves in the surrounding biofluids. And it's a process very well controlled because it's happening via surface erosion. There's no diffusion of water into the device-grade monocrystalline silicon. It just dissolves away in sort of a layer-by-layer fashion. So I got very interested when we stumbled across that and understanding the chemistry a little bit better. We collaborated with Narayan Alluru. He's a computational chemist at University of Illinois. This is a molecular dynamics simulation of the dissolution, the initial dissolution of a nanocrystal of silicon, where that particular tagged atom of silicon across this nanocrystal has dissolved into silicic acid. It's water soluble. And so you imagine continuing the simulation, you would completely consume that nanocrystal. It's totally gone, just silicic acid biocompatible end product. So it turns out the chemistry is much more subtle than this, because this is just pure water at neutral pH. In the body, the pH can be all over the place. You got proteins, you got ionic content, salt effects, all sorts of things. So it's difficult to predict precisely, but that's essentially the underlying chemistry that we're talking about. So that was 2012. We published that paper, and then kind of went crazy, because now we stumbled across an excellent choice for a semiconductor for this notion of bioresorbable electronics. Can we put around that semiconductor material all the other classes of materials that you would need for integrated circuits? So thinking about semiconductors, not just monocrystalline silicon, but amorphous silicon, poly, nanoporous silicon, silicon germanium, you want to do high-speed devices. Zinc oxide turns out to be an interesting option. You want a direct bandgap material. It's also piezoelectric. What are you going to use as the dielectric? You can use silicon dioxide, silicon nitride. Those are great choices, very standard materials in conventional electronics, but they also dissolve to biocompatible end products. Silicon dioxide dissolves to silicic acid and hydrogen. Again, silicon nitride dissolves to ammonia and silicic acid. Then what are you going to use for metals? There's all kinds of options here: magnesium, zinc, tungsten, molybdenum, iron, all sorts of materials you can deposit in thin film form. You can lithographically pattern them, etch them, and then they also dissolve in biofluids to biocompatible end products. And then there's all kinds of substrate materials that you can think about. Biomaterials like silk fibrin, we've done a lot with that. And then synthetic polymers that are also well-known bioresorbable materials: PLGA, PLA, POC, collagen, and so on. So anyway, there's been a lot of contributions from many other groups in this area of transient or bioresorbable electronics. We try to encapsulate the full body of work in this chemical reviews article. You can take a look at that if you're interested. But if you put everything together, you can develop circuits that have sort of wafer scale performance characteristics, but have this unusual, unique, defining characteristic that they completely dissolve in water at rates that are controlled by the choice of materials, and particularly the choice of material used as encapsulation. And so this was a Colpitts oscillator that we designed to dissolve very quickly. And so this was early stage work funded by DARPA for military purposes, where they wanted to illustrate the ability of these devices to be used as sensitive electronics that could be deployed in a field and dissolve away to avoid recovery by an adversary, was the idea. So you might ask, you have all these electronic materials, do you really want that in your body? And so it's something we think a lot about. And this is not a proof of biocompatibility, but just to orient you to the kinds of materials we're talking about. So in this Colpitts oscillator, we have the basic building blocks for a generalized circuit technology: an inductor here, resistor, there's a capacitor, there's a silicon PN junction diode for rectification there, and then there's a silicon MOSFET over here. It's all sitting on a film of silk fibrin. So it's a naturally occurring biomaterial that's edible, very well known, it's biocompatible. So most of the mass of this device is present as silk fibrin. But the active material is mostly magnesium and silicon. We have magnesium oxide as the gate dielectric for that silicon MOSFET. But it's not much material because these are small devices and we're talking about very thin films of material. So in terms of mass level, magnesium is only present at a 100 microgram level and silicon at a 3 microgram level. So you might ask, these elements are actually recommended part of a daily diet. So if you take a look at a vitamin tablet, it also has magnesium and silicon, a one-a-day multivitamin tablet, but actually much more magnesium and silicon than are present in that circuit. So about 300 milligrams of magnesium and 10 milligrams of silicon. So you can think about this as a resorbable circuit or a really terrible vitamin tablet, because I got to eat 3,000 of these things to equal one vitamin tablet. And you might ask, have I ever eaten one of those things? And the answer is yes. I actually did it on stage at IEDM meeting in 2013. So it just melts away in your mouth. You don't taste anything. So anyway, I'm still relatively healthy, so it's a proof of some sort. So anyway, you think about these bioresorbable devices in two ways. You can think about them in a therapeutic context, but also in the context of a sensing platform. Let me talk about the former first. And so in that case, we refer to them as bioelectronic medicines. They operate not on chemical principles like a traditional medicine. They're engineered devices, but they're like a medicine in the sense they're only present in the body for a finite amount of time before they're kind of expelled through natural excretion processes. So we have a lot of different demonstrations in this space, and I won't go through the details. We try to summarize some of the things in this Chemical Reviews article. Others have been active in this space as well, and some other things that have been published since that review article. But let me focus on just a couple to give you a sense of kind of how this plays out. And I'll start with cardiac pacemakers. So this was an opportunity that was brought to us by some cardiac surgeons associated with Northwestern Memorial Hospital, downtown Chicago. And so they came to us and described a specific clinical unmet need. And that need has to do with patients who are coming in for cardiac surgery to address either a structural failure or a valve failure. So the patient comes in many cases, that's an open heart surgery. And it's traumatic to the patient, as you might imagine. So they're at some significant risk during the seizure, but also during the recovery period, typically a few weeks after the surgery. And so what they will do as a part of a standard of care for these patients is at the very tail end of the surgery, they will place a pacing lead on the surface of the heart or inside the endocardial space. That pacing lead then is left in place after the surgical site is sutured, so it passes transcutaneously out of the body of the patient to a power supply that allows them to pace the heart in the event that during that recovery period, the heart rate drops below a threshold level. So they're monitoring the heart rate, and then they're pacing the heart as needed during the recovery period. But after the patient is recovered, you don't need that temporary pacing lead in place anymore, so you have to extract it out. And that has complications associated with that, and I'll describe that in a second. So their idea was, and they were aware of our work in bioresorbable wireless electronics, their idea was to create a device that could eliminate the need for that conventional wired-based temporary pacemaker into a device that could be completely implanted, wirelessly powered, wirelessly controlled, and then designed to offer stable operating life during that recovery period, 2 to 3 weeks. After which the device would just dissolve away, eliminating the need for a surgical extraction procedure. And so that's what we were able to do. The surgical, or the complication that they were hoping to avoid is sort of illustrated here. So here's a pacing lead of the type that they use for temporary pacing. And in this particular case, it's in an animal model. It's been in the body for a couple of weeks, and the consequence of that is that the foreign body response involves the formation of a fibrotic capsule around the pacing lead, which also connects it to the soft tissue, the healthy part of the heart. And so when you pull this thing out, you tear the scar tissue, evidently, but you also, in some cases, tear away the healthy part of the heart as well, and that can cause an internal bleed that can have serious complications for the patient. So that's the idea. You can see this non-resorbable bleed in the sort of residual fibrous tissue on the outside surface. And so that is a risk. It happens. And just as an anecdote, it turns out that Neil Armstrong passed away due to complications associated with removal of his temporary pacemaker following open heart surgery. And that damage to his heart led to an internal bleed and ultimately death. And so the idea is to use an engineering approach to avoid that risk. And this is what we put together. So this is the final device that we built to satisfy those specifications. So it involves that same kind of magnetic inductive coupling for power delivery, and then we just modulate the external RF supply to control the pacing rate. So that's basically the idea. And this is all made out of bioresorbable materials similar to those that I described previously. So we have an RF diode here for rectification. We have a smoothing capacitor over here. AC power is harvested through that coil antenna. Then it passes through these leads to interface with the surface of the heart over here to provide that pacing functionality. And then the whole thing lasts for 1 or 2 weeks and then dissolves over a period of months subsequent to that. So we demonstrated the device in small, medium, and large animal model studies up to canine models, rabbits, rats, and mice. And we also have demonstrated it in human hearts, not in humans, but from organ donors. So we get access to human hearts. So we can show we can capture the cardiac rhythm even at a human scale with those particular devices. Now you can actually combine that implanted transient pacemaker with a wireless skin interface patch of the type that I described previously, but where the patch is actually providing therapy, not just monitoring. And so in this case, we have a patch that goes on the chest, very similar to the one that I'm wearing, but modified to include an RF transmission coil. So in a completely closed-loop fashion, the device on the chest can measure heart rate. Using a system-on-a-chip computational facility within the patch itself, it can evaluate the heart rate and determine whether the heart rate is above or below a threshold level. If it's below the threshold level, then it automatically activates that RF transmission coil to engage the bioresorbable pacemaker to pace the heart back up to a healthy level. And then it stops the pacing. It can measure again and pace as necessary. So the whole thing eliminates any kind of tether to the patient and can be used, as I mentioned before, in a closed-loop fashion. So here's an example of that in an animal model. So here we're pharmacologically reducing the heart rate of a rat. You can see the heart rate begins to drop here. Here's the threshold level. The patch, which is strapped to the outside surface of the animal, is monitoring the heart rate continuously, drops below the threshold level, automatically engages the pacemaker, paces the heart back up to a healthy level, then stops pacing, looks at the heart rate again. If it's still below the threshold level, paces it back up to that normal level, and it'll bounce back and forth until naturally the heart rate recovers above that set threshold. So that's kind of the way that it works. Now, one of the disadvantages of this device is you'd always like to make the device as small as possible because you minimize the amount of transient materials that you're loading into the body. It becomes easier to surgically deploy the devices. You can imagine pacing not just at one location, but multiple locations if you had sufficient miniaturization in the devices. Now, the problem with this device is it's really size limited by the size of the receiver coil that we need to generate enough power to pace the heart. And so I had a really great postdoc who did her PhD in battery science. And so her idea was, why don't we just build a battery directly into the device itself? Why don't we use just a primary battery consisting of a galvanic cell, two dissimilar metals, both bioresorbable. You can make a battery and make it self-powered. And so we thought, well, that's kind of interesting, but then how do you control it wirelessly? How do you activate it? How do you set the pacing rate and so on? And so what we did in that case is we have our primary battery, a galvanic cell. Biofluids are forming the electrolyte. And it's an open circuit unless we expose to light a silicon BJT phototransistor. So this is a photoactivated switch that closes the circuit, activates the battery, delivers a pacing stimulus to the surface of the heart whenever illuminated by near-infrared light. And so with that kind of strategy, you can create the world's smallest pacemaker, which also happens to be bioresorbable, as an alternative, as an improved version of what I just described to you. So in this case, the skin patch, it involves, the pair of electrodes for measuring the heart rate, but instead of an RF coil, it includes a high-power near-infrared LED that can be activated and pulsed on and off to turn on and off this self-powered pacemaker. So I have a little demo box here to give you a sense of what these pacemakers look like. And I have a few in these vials. You can take a look. Smaller than a grain of rice, some exact dimensions, maybe a couple of millimeters on a side, sort of that type of dimension. And so now you can just sprinkle these around. You can mount them at multiple different locations of the heart. You add optical filters. You can do wavelength division multiplex to dressing of individual pacemakers. You can load them onto conventional biomedical implants like TAVR valves and stimulate that way. So you can instrument and add electrical stimulation capability to a whole host of devices. And these are different things that we're looking at. This is unpublished, but it'll appear in about a month or so in Nature. So with the last 5 minutes, let me give you a sense of a couple of examples of bioelectronic sensors. And ultimately, maybe you combine the sensors with the therapeutic function and develop fully implanted bioresorbable closed-loop systems in the future. I won't give you, overview all the different things, just give you a couple of examples. And this really resonates with things that Alan and I have talked about recently, particularly in the context of recovery from a GI surgery, like a bariatric surgery. And so this opportunity was brought to us by GI surgeons at Washington University's Medical School in St. Louis. And so if you undergo a surgery like this, where you're basically resecting part of the stomach, what happens is you cut away the unwanted part of the stomach, and then you suture the surgical site closed. Now, the risk is you develop a leak at that suture site. And if you leak GI fluid into the intra-abdominal space, that can have very, very negative consequence for the patient. You can't see this, however, with CT imaging or MRI or ultrasound imaging. And so what they wanted is a resorbable sensor that would allow them to measure whether a leak is occurring or not. Again, in that post-surgical recovery context. You don't need the device forever, just need it during that risk period, and you would like it to dissolve away. So our first stab at this involved this particular architecture. So we have a pH-responsive hydrogel that changes in its physical dimensions upon exposure to a reduction in the pH of surrounding fluids. And so what we've done is we've embedded an inductive coil in that hydrogel. So the inductance depends on the extent of expansion of the hydrogel and thus the pH of the surrounding biofluids. And then we couple that inductor to a fixed capacitor. So we have an LC oscillator where the frequency is dependent on the surrounding pH through that expansion mechanism in the hydrogel. So I won't go through the details of the chemistry, but that's sort of the way it works. So those are the experimental measurements in the material system, and then we have full finite element modeling of the expansion. The design challenge here is how do you spool out a filamentary inductor trace in a hydrogel in a way that doesn't mechanically constrain the natural expansion that happens upon a reduction in surrounding pH. So you can do that, and it's back to the filamentary designs and so on, and that works pretty well. So we demonstrated that in small animal models, large animal models, in terminal experiments, and you can do that, and it works. You can simulate a GI leak, and then you can wirelessly read out just through reflection using an antenna and a VNA the change in frequency. You can model that change in frequency and connect that to local pH. Now that works, but it is a piece of electronics, so there's some engineering level of complexity there. What is more of a severe practical concern is just the overall range, because it's near field coupling between the interrogating antenna and the implanted sensor. So I think this can work, but it will require some additional electronics development on the reader side of the system. I don't think you'll need to change the sensor itself, but that's an ongoing effort. What we realize, there's actually a much easier way to do that. And thinking about translation, especially in the context of transient electronics, you want something that's very simple. If you want to get started down that path. We love pacemakers, but that a lot of challenges with that in terms of FDA and regulatory approval. So this is the simplest transient device that we could conceive of that's addressing a real clinical need. And so what we do here, it's not even a piece of electronics, it's that same type of hydrogel chemistry, but instead of embedding an inductor and trying to do wireless RF readout, we include in that hydrogel matrix just small discs of resorbable metal. Like tungsten or molybdenum. And that metal provides ultrasound contrast. So we can implant this down at a targeted location in the body, and we can just use B-mode ultrasound imaging to read out the size of the device using these small discs essentially as a ruler. And so we can just measure directly by ultrasound imaging expansion of that hydrogel, thereby affording a level of chemical specificity to ultrasound imaging. And of course, in a platform that itself is bioresorbable and can be scaled to very tiny dimensions, limited ultimately just by the resolution of the ultrasound imaging system. So that works really well. And so we have chemistries that allow for measurements of reductions in pH. The GI leak would be important there, associated with protonation to deprotonation of these terminal amine groups. And then we have other kinds of chemistries that can be used to measure an increase in pH using carboxylic acid groups in the hydrogel. So we can kind of go in both directions, and those two material classes address different kinds of clinical needs in that surgical context. So this is one of these devices, just a benchtop study. You can see the magnitude of the expansion. There's a lot of optimization around this. You want the devices as thin as possible to limit time delays associated with diffusive transport and equilibration with surrounding biofluids, but you see a very, very clear dimensional change there. And of course, all of the materials, including the hydrogel, are designed to resorb naturally in the body to eliminate, again, that device load on the patient after the device and the measurement is no longer really needed. So the nice thing about these devices, they're super simple, they're tiny, they're flexible, they're soft. You can deliver them with a syringe, for example. We have a suture site over here that allows us to mechanically fixate the device to a targeted location. We also have bioresorbable adhesive chemistries that allows us to sort of glue these devices onto a soft tissue surface, but this is kind of what they look like. There's deployment. That's kind of the ruler. Read that out by ultrasound. It's compatible with laparoscopic surgeries as well. And so this is what it looks like then in an animal model. This is a rat model. So there are the 3 bright spots associated with 3 of the discs in that sensor platform, and you just measure the separations to determine the extent of expansion and therefore the local pH. But like those very tiny pacemakers, these small devices can be sprinkled around, and so you can get not only individual site-specific measurement of pH change, but you can also develop a spatiotemporal mapping. So there's a promise then of being able to detect not only the presence of a leak, but the location where that leak is occurring by deploying a number of these devices. And again, we do all the foundational engineering to understand the underlying mechanics. This is all FEA modeling in comparison to benchtop studies. So that works well in small animals, and there's some details here that I don't need to go through. Chronic studies as well. And then large animals works quite nicely because you get extreme depth of penetration and measurement capability associated with ultrasound by comparison to near field RF readout, which I described previously. So we've been able to effectively measure measure the dimensions of those structures at depths of around 6 centimeters, so probably as deep as you would ever need to go in the context of a human clinical application. So that's it. That's all I had for you today. I apologize if I went on a little bit too long, but I try to give you a sense of what we feel like are some frontier kind of developments in bioelectronics. Again, we're just one group, a lot of other groups, including Adam's group here and other activities at University of Edinburgh. But we've been interested in sort of soft skin-like electronics, this bioabsorbable electronics, where we have clear paths and connections to clinical needs. And it's really that collaboration with the medical school that drives a lot of our priorities around engineering opportunities. So we're very collaborative, obviously, not only with the medical community, but across areas of engineering science as well, and sort of list some of the key folks here. But the most important people are the students who actually do the work. I just get to talk about it. So I've been blessed with really fantastic students and postdocs over the years. This is a picture of the group from a recent holiday party just here in December. And so I always like to conclude my talks by acknowledging their hard work, their great ideas, and by thanking you for your attention. I'd be happy to answer questions if you have any.
Okay, thanks, thanks, John. I teach bioelectronics to undergraduates, and I often start with the sort of idea that electronics came from bioelectronics, the observations from Galvani and Volta and these guys. And it's interesting to see just how far the field has come from those sort of early days of observations to the sort of thing that John's talking about here. I'd like to open the floor to questions. Does anybody have burning questions? Catherine? What we'll do is, shall I just walk around with the microphone rather than throwing the box to people? Okay.
Thank you. Sorry for not taking the one that gets thrown, but I don't want to concuss my neighbours by dropping it. So, yeah, thanks for a fascinating talk, John. I was just wondering, could you say a little bit about how some of these devices are powered and any unmet challenges in terms of energy and power for the things that you're developing, please?
Yeah, so we had several discussions about electronics and efficiency and power. It's always a problem, where's the power going to come from? What are the power requirements for the devices? So I think low power electronics is a very important future, not only for conventional applications, but any kind of integrated bioelectronic application as well. Power harvesting turns out to be a really interesting and compelling topic, and we and others have been thinking about that and working in those directions. You think about harvesting from mechanical motions or thermal gradients. Photovoltaics, obviously, sometimes can be relevant. For our devices, we're like, trying to use whatever, works. We're not fixated on one particular approach. We're happy to incorporate ideas from other groups or just try to piece it together so that we can address real kind of meaningful practical requirements in clinical care. So I stepped through a number of different devices that use different power delivery and power harvesting schemes. So the first platform is that full kind of kid's tattoo-like electronics, no battery. So we're doing wireless power transfer. And there are disadvantages with that because you have a limited range. So you can operate over about a meter or so. So it's like an RFID tag type reader. So it's a transmission antenna. We like 13.56 megahertz because it's sort of an industry standard. We'll run the transmission antenna at a few watts. And then the devices only need maybe 10 milliwatts to operate, maybe a little bit lower than that, depending on the wireless communication scheme. We started with NFC SoC technology. So you don't need tremendously high efficiency in power transfer because you're not really limited in that sense. In a hospital environment, just plug it into the wall. You have as much power as you need in the transmission antenna. At 13.56, there's almost no tissue level absorption. So there's very little risk to RF exposure. There are guidelines, and we kind of follow that, but you can drive the antenna pretty hard without getting any near any kind of limits, which is different than if you're operating at higher frequencies in the gigahertz range. You get a lot of water absorption. That becomes a problem in terms of parasitic heating. So that would be one example. The second example, which sort of followed on that first demonstration, where we really didn't have to worry about cost, because if you look at NICU care currently, all of the sensors are just single use. Even the NIRS sensors are $200. You put it on, you use it once, you throw it away. That's just the way it works in hospitals in the US, probably here in the UK as well. Because the cost of operating the NICU and providing the overall care is such a dominant consideration in the cost of the care of the patient that the sensor cost is negligible. So that's how we got started, is really thinking about single use. So we didn't have to worry about robustness from a multiple cycle of use standpoint. We also didn't have to worry too much about power supply because a reliable source of wall plug power, and we can kind of do that. 1 meter is also good enough because you're in the context of an incubator. You know where the baby is. It's not jumping in. So it's a kind of confined space, so it's a good match. When the Gates folks approach us, it's a totally different set of considerations. Now you're talking about operating in countries where there is no reliable source of wall plug power, so you really can't think about a transmission antenna for that reason, but also because of the engineering complexity associated with adding that kind of hardware. So you really need onboard power so the devices can operate independent of what's going on in the surroundings. So for the devices that I was passing around, they're very tiny lithium polymer rechargeable batteries. So they're wirelessly recharged. So we don't need any plug ports or any places which could serve as a nidus for bacterial growth and complicate aspects of cleaning and reuse. So that's the power supply in that particular case. It leads to a form factor that's more like a Band-Aid and much less like a kid's temporary tattoo, but that's what was required, and so we kind of do that. We could retain a lot of the soft mechanics, so it's not a tattoo form. So as an engineer, we're a little disappointed, but the nurses didn't seem to care. It's a good device, and it's flexible. It's a lot softer than things that they're used to using. So that's what we did. We also designed it to allow mini cycles of use because you have to do that to amortize out of the cost of patient monitoring per day, the cost of the device itself. So you need it rugged enough, it can be used hundreds of cycles. So that's a different power supply strategy. And then the final example was in this galvanic pair that serves as a primary battery for that very tiny pacemaker. That's kind of the third sort of power supply. So it doesn't need to be rechargeable because it's a resorbable device and it's temporary, lifetime anyway. And so we just use that primary cell for that application. But I think there's a lot of opportunities in further reducing the power requirements for the electronics. Smaller batteries always better, for instance, and it just opens up different kinds of options. And likewise, as I mentioned, a lot of great opportunities for doing additional research in power harvesting, from the kinds of sources I mentioned before. So different topics in that space, I think, great directions for research.
Okay, thanks for that, John. Where should we go next? Alan, let's go to Alan, and then we can go to Soto.
So I'm talking to the cube. Okay, good. Thanks, John. That was a great talk. You reminded me of something we talked about this afternoon, which is regulation, which gets worse the further you go into the body, I suppose. And something you said is just now reminded me of something I'd thought about earlier, which is that we are releasing things into the body which may eventually be toxic, and medical regulation is going to worry about that. But homeopathy has been doing that for a long, long time. Yeah. Do you think medical regulation will catch up with that concept that small quantities of toxic materials may actually be very tolerable?
Yeah, that's a good question. I guess there's always sort of a dose level that would become problematic, even for materials that are nominally biocompatible. You have too much of it, right? Could be an issue. So there's sort of dosing limit in that sense. We've done a lot of histological studies, as you probably know. We've done a lot of blood work to look at where these various elements are going over time after a device is implanted. So you can track silicon, you can track magnesium, you can look at tungsten, for example, as it resorbs. You can see different elemental content of those species in different organs harvested at different time points from animal models. So you can sort of track where it's going and how it's being expelled. And so we don't see any persistent buildup of any of these constituent materials in any of the vital organs. They're all ultimately excreted without any trace residual amounts. We don't see that. And so I don't think any of the materials that we're using are intrinsically toxic. They might be extremely high loading levels or something like that. But electronics is, for the most part, miniaturized by design because of the performance benefits that follow from that. And the good news is it also limits the amount of mass content of these materials that you're putting in the body. So it's a great synergy in terms of size scaling for electronic performance and size scaling from avoiding any kind of adverse effect associated with the dissolution of the materials. So I think your question is a good one, but we've just avoided toxic materials entirely. I would say as an addendum to that answer is that we don't have a good bioresorbable LED. And so we thought about gallium arsenide. Arsenic is not going to be a good thing, but maybe, as you point out, if it's in sufficiently small amounts, then you could do light sources. We've made LEDs out of zinc oxide, but they're really terrible LEDs. Gallium nitride is not really resorbable. So in that compound semiconductor space more generally, there could be a need or an interest in asking this question, is what happens with trace amounts of toxic materials? That would be an important one, but we haven't had to grapple with that too much, but it could be interesting in that context. Yeah.
John, thank you. Really fascinating talk. A slightly different angle to Alan's sort of question. You mentioned, of course, silicon electronics are really great for the longevity, but also, achieving optimum performance in a sustained sort of fashion, over a long period of time. But you're trying to do, obviously, the opposite here.
Yeah, right.
You have biodegradable electronics. Yeah. So I was wondering if you can comment on the degradation of the performance and how do you compensate for that, especially within needing to ensure that, you operate in a medically approved sort of regulation environment.
Yeah, I didn't say too much about it. I'll come back and maybe make a couple of comments. So this is a very good question. I get this question a lot, is like, if the materials themselves are dissolving away, won't that lead to a drift in the electronic performance? And don't you need to design to anticipate that drift so it doesn't have any adverse effect on the overall desired operational characteristics? And the answer is we don't even try to do that because I think it's very difficult, maybe impossible, because you can't necessarily engineer for an anticipated, well-defined chemistry in the surrounding biofluids. And you don't know about the effects of protein buildup, all sorts of uncertainties. You're not going to know how quickly the materials are dissolving with sufficient accuracy to allow you to design a circuit to anticipate that dissolution. I think it's impossible. So on the benchtop, you can kind of do it. You know exactly what the chemistry of the surrounding fluids are, but in a real application, I don't think you can. So instead of trying to do that, modulate the thickness so that you can accommodate some level of dissolution and you hope the drift isn't sufficient to cause the device to fail, instead of doing that, we design so there are two timescales. One is, what is the timescale for stable, reliable operation? That needs to rigorously satisfy the clinical use case. You can't compromise in that. Then the other timescale is, how long does it take the device to disappear entirely? That's much less rigorously and strictly defined. That could be 3 months, 6 months, 9 months. Doesn't matter as long as it's going away. But that operational time frame is super important. And so what we try to do in our devices, all the ones that I described to you, is we define the stable operating life by the choice and the thickness of the encapsulation layers. So these are bioresorbable materials, but they're designed to be barriers to surrounding biofluids. So as soon as those encapsulating layers are compromised, either by just thickness reduction and dissolution or formation of pinholes or whatever is going to cause biofluids to penetrate down through that encapsulation structure and begin to dissolve and corrode the active materials, we're assuming we're not attempting to operate the device at that level. So you can put different kinds of sensing elements within the device to identify the time at which that encapsulation layer has been compromised. Once it's gone, we're not trying to operate the device anymore. So if you think about it from a materials standpoint, that encapsulation layer is critically important. And so it's not the sexiest kind of thing to work on. You want to work on the semiconductor or the devices or whatever, but that encapsulation layer is challenging because it needs to be made out of material that will ultimately dissolve completely. But meanwhile, before it's dissolved, it has to be a perfect biofluid barrier. That's really hard. And so a lot of the work that we're doing now is to try to define that layer. We can, the chemistry and the thickness and the design, we can do pretty well for stable operating lifetime, 1 to 2 weeks. We cannot do 1 to 2 months. That's hard. And so for a bone stimulator, for example, you'd like it to survive for the time scale of the fracture healing process, could be 8-9 weeks. We can't do that right now because the encapsulation layer is just not good enough for that. Yeah.
Thanks, John. If we have time for one more quick question and answer from Sotos, if that's okay, and then we are going to go to having some drinks afterwards. So if there's more questions, then please come and find John at the drinks and ask him questions, okay?
I got more devices if anybody wants to.
I promise it's going to be very quick. You mentioned through your talk a lot of times the words engineering, design, properties, optimization of what the property of the material or the property of the device that will be. And a week ago, Google announced the co-scientist, an AI basically that helps together working with a scientist as a way to accelerate. Ahead, 5 years from now, how will the lab look like?
Yeah, hopefully we won't be put out of a job by AI systems. That's a really great question, and I guess we're pretty deep into AI for data analytics. We're not experts, but we just use kind of the tools that are available. A lot of other groups do as well, but I think in the context of sort of biophysical and biochemical sensing measurements, how do you connect those data streams to health outcomes or labels around patient status? I think that class of problem can't be addressed with traditional physics-based engineering approaches. And so I think it's a great match for neural networks, that kind of thing. And so we do a fair amount of that. So I think that aspect of the research will really change what we can do in terms of patient insights, predictive assessments of health trajectories from instantaneous measurements using population scale training sets, this kind of thing. I think it's very powerful. And I think the ability to capture diverse data streams in a common data format in a hospital setting with physician labels attached to that data over time will be a tremendous resource for training AI systems. So we're very much engaged in that. And actually, Ewan's been a great collaborator in that, looking for early signs of patient complications. And we're just at the very beginning of that process. But I'm very excited about it because it allows this data to be used in a very powerful way that could improve patient outcomes, reduce risk, allow for early admission, all that kind of stuff. So that's one. The other is more at a nuts and bolts level of how you do circuit design and how you do printed circuit board layout and all that kind of stuff. Software, there's a lot of software and firmware involved in these devices. So we have a couple of staff software engineers associated with our institute. And so they're fully into the kinds of tools for automating the generation of code and graphical user interfaces and, like I said, circuit layouts and stuff. It's so powerful. I mean, a lot of people have had experience with it, but it takes a job that would take 2 weeks down to 2 hours. That's what my software guys tell me. So orders of magnitude. So those two, we're not using any kind of AI for materials level development currently. I think that's more challenging. I'm not sure how that will play out. Maybe a little bit of guidance here and there, but those two examples I gave you are here and now, and they're definitely changing the way we do things.
Okay, thank you, John. So with that, I'm going to close the Q&A. But if we could, just in closing, John has been one of my scientific heroes for a long time. I've followed your work really, really closely. I think we're really lucky to get John to Edinburgh. I'd like to say thank you to David for facilitating all of this. Thank you to John for coming and delivering such a great lecture. And let's do one more big round of applause, and then we'll move into the atrium for drinks. Okay, thank you.